So let me say a few words to wrap up this sampling method that we started last time. Used sampling and using law of large number to prove approximate Carathéodory theorem. So in this paper, it's lecture 27. There are some algorithmic applications of this. Let me just briefly mention approximate Carathéodory theorem. One is they used it to find approximate Nash equilibrium in game theory. Some algorithmic application. Approximate Nash equilibrium. And also they use it to find approximation algorithm finding dense subgraphs of fixed order. Approximation algorithm for finding dense subgraphs of fixed order. There's another approximation in similar spirits is to approximate doubly stochastic matrix. So let me just briefly mention it. It's also in this paper. There's a theorem by Birkhoff von Neumann for doubly stochastic matrix. Basically, what this theorem says is that every d by d doubly stochastic matrix, meaning that row sum, column sum is 1 for each row and column. For any d by d doubly stochastic matrix can be written as a convex combination of d by d permutation matrices. Can be written as a convex combination of permutation matrices. Then we can also have approximate version, approximating epsilon close in entry-wise, meaning in the infinity norm. So approximate version means we can use big O of log d over epsilon square, meaning permutation matrices. To approximate epsilon close every stochastic matrix, epsilon close entry-wise. If you're interested, you can refer to the original paper of Barman. Right. Now, there are some similar applications of this idea of sampling in various different areas, but they are basically of same flavor. Just you do sampling, IID sampling, where the expectation is the object we want to approximate, and you use some sort of law of large number, some inequality, like Khinchin's inequality we used last time. And all of these has some origin. One of the earliest applications is this Morae's lemma. This is the sampling and one of the first appearance in functional analysis. Here, let's see another thing, similar flavor of approximating some functions on abelian group. So let me state the theorem. Here. So what's known is that if we have here's the setting, another thing of similar flavor, approximating functions on abelian group. Suppose we have some abelian group G. Here's the setup. We have some, let's say, finite abelian group. Okay. Now, so let's take this as granted, granted if you don't know the background. So we have some finite abelian group, and there is something called the dual group, which is isomorphic to the group itself, consisting of so-called characters, where the elements are called characters. And what's useful about this dual group is that for every function defined on the group, so suppose we have a function which is a function that takes assign a complex number to elements in this finite abelian group, then by this discrete Fourier analysis, we know that we can express all such functions as a linear combination of characters from this dual group G hat. We can express F as a linear combination, so of some, let me say, Ci gamma I. Okay. Let's say we order the, let's say G and G hat, they each hold size n, order n. Why not? So let's order the characters as gamma 1 to gamma n. We can write it as these, where actually these, let me not write it like this, sorry. We can write it as C gamma, which is a complex number depending only on gamma. Well, I can write it directly. This is something called the Fourier coefficient times gamma. So if you don't know what it is, it doesn't matter. We don't need to know it. This is just some complex number depending only on gamma. Okay, just think it this way. This is some complex number depending only on gamma. And you range over all gamma in the dual group G hat. So we can express it linearly. Now, if you can express it linearly, again, this set of coefficient, this sort of linear combination will induce a probability distribution over the dual group G hat. So what we do is we take the norm of these complex numbers, coefficient, and then we just sample gamma proportional to this the norm of this uh, com combination coefficient. So what we do is we can then write this as let's take its norm. So it will become a real number. We can then sample proportional to this real number times when we take out the norm, we have to multiply by the rotation. Let's record C sub gamma to be the rotation. So here, this is a number with, this is just a rotation as norm 1. Okay. So we can write F as gamma in G hat. This number times C gamma times gamma. We can now define a probability distribution where let's take a random and define a random sort of twisted character chi such that we take chi to be this twisted, meaning multiplied by this rotation C sub gamma times gamma with probability the norm, the length of this Fourier coefficient, we choose it proportionally. So we normalize by sum of all such number. Okay. Now, if we do this, you notice that this is exactly the same as how we sample in approximate Carey-Theodori. What do we know about this random character? We have in expectation, the expectation of this random character chi equals to what? We sum up all gamma in G hat, the probability that okay. So actually, let me normalize we can do normalization. There's no harm doing that. So that the little L1 norm, so that this is 1. We can do normalization. Such that this equals to 1. So then this probability of chi equals to C gamma gamma times gamma, right? Which is nothing but just this thing, which is F. Equals to F. So now what's the catch here? The important thing is that originally, by discrete Fourier analysis, we know that for every function on the group, we can write it as some characters, these characters using what? Using n characters. You could use up to n, where n is the order of the group G. But now we want to, this n could grow to infinity, right? We want to use, we want to write it in an efficient way using few characters. So can we use something independent of n? That's what we want to do here. You sample this random character chi, IID copy of that, and we know the expectation is the function we want to approximate. So as long as the number of samples you take is large enough, we can approximate in LP norm close to this function. It's the same as in the Theodori. So let me just state the theorem without giving the proof. The idea is the same. So it's theorem of approximate functions using few characters. So we have, again, some p norm we want to approximate. Epsilon is the error, how close we want to approximate this function. And then we have function normalized so that this is 1. So this is nothing but the little L1 norm. Write it in the compact way is the 1 norm of it is 1. Then we can find, then the conclusion is there exists k, which is at most some constant, times p over epsilon squared. You see, it's the same form, characters. Gamma 1 to gamma k in G hat. And C1 to CK. This is the rotation. Such that we can approximate F by the sample mean Cj, gamma j. Now let's approximate it in the LP norm in up to epsilon distance. Okay. So I will not prove this. As I said, this is basically the same proof. Let me just state the tools that we need. The more general form of this Khinchin's inequality. So the general form is the following. We can state it for this application, we need something for complex valued random variable. So here's the lemma, so-called Marcinkiewicz and Zygmunt's inequality. Setup is the following. We have, again, some number p, at least 2. And suppose we have x1 to xn, independent random variables, mean 0, complex valued, independent, mean 0, complex valued random variable. Okay. With uh okay, let me state the um general form. It you can with the pth moment finite. Then what we have is this inequality. Expectation you look at the sum, um, oops, look at the sum of these samples. That's the random variable looking at the sum, and take look at its pth moment is at most some constant, absolute constant c times p raised to the power p over 2 times the expectation of this term, which is the p over 2th moment of this random variable x j squared, j from 1 to n p over 2. Okay. It looks a little bit complicated, but maybe let's look at a special case to understand it slightly better. Look at the case remark, p equal to 2. When p equal to 2, what do we have? Look at the left-hand side. Left-hand side is, because this is mean 0, right? So if this is 2, this is basically the variance of the sum of this random variable xj. So left-hand side is the variance of the sum of independent random variables x1 to xn. But what is right-hand side? Well, forget about this term for now. Here, 2 divided by 2, so you can forget about this part, right? You can forget about this part. And here, inside linearity of expectation, you can exchange the summation expectation. Is basically the sum of the second moment, the expectation of these. Second moment, this is mean 0, so that's variance. So it's the sum of variance. This is the trivial identity we mentioned when we talk about second moment before. The variance of sum of independent random variable is the sum of variance of each one of them. This is sum of variance of x1 to xn. So when p equals to 2, we don't even need this term. Okay. And this inequality is saying that this sort of variance of independent sum of independent random variable equals to sum of variance of independent variable. Similar bound holds for higher moments with the cause of some small constants that we need to multiply. Okay. So this MZ inequality up to some constant factor for higher moments. Okay. So we will not prove this general form let's look at a slightly more special form for real valued random variable, where we assume each random variable in absolute value is bounded by 1. In this case, we will see that this inequality is basically saying law of large number. So let's see the special case. And this special case is a simple proof. We can prove that. Here's the lemma. This is another form of Khinchin's inequality. Suppose we have p at least 2 and x1 to xn independent random variable. X1 to xn independent random variable. Now it's real valued, so let me not mention it explicitly, with mean 0. And bounded by 1. Then there is this absolute constant c, so that we have the following. We have the expectation. If you look at the average of this random variable, oh, right. The pth moment is at most some absolute constant times p divided by n raised to the power p over 2. Okay. So before proving this, let me again write a remark. Why this is law of large number nature. Because what do we know about xi? We know xi, each one of them is has 0 mean 0. So the average of them, again, their expectation, their mean is 0. Then if this random variable, now look at the average as a random variable, has mean 0. Since it has mean 0, we would expect that its pth moment is also pretty close to 0, which is the case when n is sufficiently large. This is the sample size, right? Larger than p, this guy goes to 0. Okay. So this is saying the this is the average, which is this random variable. This sample mean the sample mean is pretty close but in LP expectation, the pth moment, to its actual mean, 0, provided that the sample size which is n, is sufficiently large. Okay. Any question? So I have time to prove this. Maybe I'll skip this proof for now. The proof of this is not hard. If I have time at the end of this class, I will sketch a proof. For now, let's leave it as exercise. I want to move on to other material. Now, let me just, to end this sampling part, let me just mention one more important results of flavor similar to this approximate Carey theory. Okay. There's a development called a spectrum sparsifier for a graph. So let's define the necessary things that we need. Spectral sparsifier. Okay. So the thing we want to approximate now is the Laplacian matrix of graph G. So we have the setup is we have a graph G. The Laplacian matrix LG is nothing but just its adjacency matrix A. Oh, sorry. You take a diagonal matrix where the diagonal entries are the degree sequence of the graph G and subtract from it the adjacency matrix of G, where BG is the diagonal degree sequence matrix. And AG is the adjacency matrix. We can also write when G consists of a single edge, we can write Laplacian for a single edge. So we write LE for fixed pair that's been an edge, E for the rank 1 Laplacian for the edge E. Okay. In this language, then we can compute for a vector of length, the order of the graph G, this quadratic form, X transpose Laplacian matrix of G times X. This, if you expand it by linearity, Laplacian of G is just the sum of Laplacian of every single edge, all these rank 1 matrices. So sum over all edges in the graph, X transpose LE times X, right? This can be easily computed. If it's not clear, I'll leave it as exercise. The sum over all edges, E, let's say E has n vertices UV. XU minus xv square. Now, why is this quadratic form interesting? It actually, if you take x as the characteristic vector of the subset of vertices, this quadratic form is exactly the size of the cut, where one part of the cut is this set. So, this quadratic form corresponds to cuts in graph. Here's what it means. For any subset S of vertices, the size of the cut, what do I mean cut size? It just means number of edges in G with one endpoint in S and the other endpoints in the complement of S. Okay? This is just the characteristic vector of S transpose times Lagrangian of G times characteristic vector of S. It's the quadratic form above. So here's the very quick background. Now in TCS, in computer science, a lot of time when we're given a graph G, we want to have the G could be very dense, has lots of edges, which means it's very costly, very expensive to design algorithm on dense graphs. What they want to do is to find the substitute, a sparse substitute with few edges, so that this sparser substitute, in terms of all different cuts, it can approximate the original graph pretty well. Okay. Now, that's the original form of cut sparsifier. And now we're going to do this more general form where we find a sparse graph which approximates the Laplacian of the matrix pretty well, which then, of course, also preserve the cut because of this relation. So the spectrum sparsifier is more general than cut sparsifier. So what we want to do, let me write it down. So originally, what one cares is cut sparsifier introduced by Benzur and Karger is a sparse graph that approximates the original graph G in terms of cuts. What it means is that we want to approximate EGS S bar for any S. Okay. Later, Spielman and Teng introduce a more general notion, this notion of spectral sparsifier that I mentioned. Spectral sparsifier. This is by Spielman and 10. They introduce, what it means is a sparse graph G prime is a spectral sparsifier of G if it resembles spectrally as follows. This quadratic form we want to approximate equals to 1 plus minus epsilon times the Laplacian of the spectrum sparsifier times x for all x, for all vectors. Okay. Here, just quickly, what does this mean? 1 plus minus epsilon. It just means it's at least 1 minus epsilon and most 1 plus epsilon of that. The theorem they prove is by Spielman and Srivastava. Is that we can find a weighted spectrum sparsifier for any graph on n vertices with only n log n edges. So it's almost linear number of edges. So the original graph G could have quadratic number of edges, but we can use a very, very sparse one, weighted one, though, to approximate it spectrally. So for any n vertex graph G, there exists a weighted spectral sparsifier with some constant times 1 over epsilon squared times n log n edges. Okay, so that's very sparse. And the idea of this, let me put remark, is what you may imagine. So our graph G, our Laplacian, is the sum of this Laplacian of rank 1 matrices. Then what they do is basically randomly sample edges E according to some distribution. And this distribution, some distribution, let's say alpha, this distribution is derived by so-called effective resistance. One can define something. It's basically just if you view the graph as electronic network, the resistance when you inject 1 unit of some electricity, and what's the resistance from the ends of these two end vertices of an edge. So according to some parameter, one can sample this edge E. Now, such that the expectation of this random edge, this random sampling in expectation is the same as the Laplacian of the original matrix G. So now it looks very familiar, right? We want to approximate this Laplacian LG, and we are sampling something, some L random Laplacian, such that in expectation, this guy is LG. Now you sample IID copy, L1 to L blah, 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 sufficiently many copies. Then you use some sort of law of large number. Now the concentration inequality, you need to use some Chernoff type inequality for matrices instead. And that's the whole idea for this n log n bound. So this is the proof uses random sampling where effective resistance and matrix Chernoff bound. Okay. One remark is that the log n term is needed if we do things randomly, if random sample are used. There's a follow-up where later it turns out there's a deterministic way of choosing sparsifier which can remove this log n term. That's something else, not using sampling. This is one of the breakthrough by Bateson, Spielman, Srivastava. Who proved the existence of sparsifier with remove the log n term. Okay. But this n log n bound is the same idea as with what we have seen. We want to approximate something, in this time, a matrix. Then we define some random matrices in which in expectation is the matrix we want to approximate. So we're going to sample many IID copies of this same distribution as this random matrix, so that we hope the average, sample mean of these random ones will approximate well our original Laplacian. And to bound this, we use some Chernoff bound for matrices. Okay. All right, so in the remaining time, maybe let's prove this Kinchens. I want to actually talk about something else, but I don't think we have time. So let's just finish the proof of this Kinchens inequality. Where is it? This one. Right. Maybe this can be even at least one. Let's see in the proof. Check. Okay, one or two. Probably one is okay. The first thing to notice is nestiness of the moment, the LP norm. So what we want to prove is wait. Right. So the first thing is nestiness of LP norm, which follows basically by convexity, Jensen's inequality. What it says is that if we have some number p and most p prime, then the LP norm is increasing, the capital LP norm. So the expectation of x to the p, 1 over p is at most expectation x to the p prime, 1 over p prime. Okay? Right. Using the nestiness, so what do we need to prove? Let's look at here. What we need to show is we need to show, let's take pth root on both sides. Then the left-hand side, just the LP norm of this average. We need to show the pth root is at most C P over N, take a square root, right? This P disappear. It's 1 over 2. So it's this guy. So by increasing this constant C a little bit, we can replace P by P prime because this is at most, look, this is at most this. So it's enough to prove this is at most, let's say, C prime over N. And this, if P is odd, what I'm saying is if P is odd, we can replace by P plus 1, which is even. Let this to be P prime. So let's prove for some constant C, this is true, then it will imply for the original P, let's say C times P plus 1. You can replace just by 2C times P. What I'm saying is, at the expense of increasing C, so up to increasing the constant C, we may assume that P is even. We may assume by rounding P up to an even integer, that P is even equals to 2m is even. So now P equals to 2m. Let's say 2r. Is it better? Yeah, maybe. It's even. Okay. Now let's write down the thing we want to prove. We want to bound. We look at the pth moment, right? So the expectation of the pth moment of the sum xi, I from 1 to n. Pth moment is 2rth moment. Since now P is 2r, which is an even number, so the absolute value we can change to just parenthesis. It's the expectation of sum of xi 1 to n 2r. What is this? This equals to, if you expand it, this is basically the sum of expectation of products oh, maybe I don't need this. The product of xi, j from 1 to p, then you have I1 to IP, which is sampled from N. Okay, ranging over all possible choice of sub-index, p-tuple indices, each indices ranging over 1 to N, just expanded. Now, what's important is, if you look at each term of this summand, what do we know? Each random variable is centralized so that the mean is 0. And xi, xj, they are independent of each other. So that means whenever we have, you can write this as some xi to some power, xj to some power, xk to some power, right? Whenever you see a power being 1, because of the independence, we can split this out from the expectation. And the expectation of this one term, linear term, is 0. It vanishes. That means we only need to look at the terms where each indices appear at least twice or 0. So let's write it out, what I just said. Recall as xi's are independent and the expectation is 0 for each one term. We have expectation of xi, xj. By independence, we can split them, is 0 for any I not equal to j. Okay? This means, this implies in this summand, or if a term has a power, how do I say? If some x1, xi, which is in x1 to xn, appears exactly once in this product, then this term vanishes, right? Has some xi appearing exactly once, then it vanishes. Okay? In other words, only terms with every random variable xi appearing either 0 times or at least twice survives. With each xi, I in n appearing 0 times or at least twice survive. And for each one of these terms, if you look at in this summand, because xi is bounded by 1, each one of these terms is also at most 1, right? Furthermore, for every I, So this pth moment is all these terms survive, and each term is at most one. This implies each term in this is at most one. So thus, this is at most the number of, let's write it, the number of p tuples. So we have p indices is the number of p tuples I1 to IP such that, and this p tuple is in n to the p, where each index appears zero or at least twice. Let's compute this number. Okay. Any questions so far? Only this time, this type of term survive. And for each one of this term, because our random variable is bounded by one, you can bound each term by one. So this summand is at most number of such terms, number of such tuples. And this number of such tuples is easy to bound. Number of such tuples, I claim that this is at most, well, it's at most, how do we bound it? Can be upper bounded as follows. First, let's fix the choice of I1. And the number of ways to do this is n choices. For this step is n, right? You can choose an arbitrary index for I1. Now, once you choose I1, I know this index at I1 must appear at least one more time elsewhere, because every index must appear at least twice. So then we have to choose some other position so that this index in I1 appears again. Then we need to pick another index, pick another position, some j, some ij in here to assign the same value as I1. And the number of such choice is p minus 1. Okay, you have p minus 1 positions. And then we repeat. Move on to the next index, I2. Maybe I2 is the one that picked here. If it's already determined, then just keep moving on. If it's not determined, so if I2 not already assigned the value, then again, choose some value for I2. And the number of such choices is again n. Okay. Then we know I2's value must also appear somewhere. This I2 value must appear at least twice. But what if I2 pick the same value as I1 and I1 picks? Let me first write it down, and then we do the same thing. Pick another position to pair up with I2. And the number of such choices is P minus 3 now, because 3 things get kicked out. I1's pairing, I2. So you have P minus 3 choices. Then carry on, dot, dot, dot. So the total number of choices, P tuples, is at most, you choose n choices for half of the indices, P over 2, each one of them. You choose arbitrarily, and you need to do pairing. So the first pairing is P minus 1, second pairing P minus 3, P minus 5, dot, 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 all the way down to 1. So this is at most n times P to the P over 2, which is exactly the thing we want to prove, I think. N times P, right. N times P to the P over 2. And we are doing the sum, right? So you need to multiply n to the P on both sides. That's this thing. Okay. This will finish it, the proof. So I just need to convince you this pairing will not, we don't have problem here. So what I'm worried is that maybe the value of I1, let's say in the first coordinate, you pick 1 value, and then 1 value also appears here. Okay. And you pick IP as this step to pair up the value 1. So now you move to I2, and I2 is not assigned. So you assign some value 1 to n. Again, you assign 1. The problem now is that you don't need to pair up I2. But probably this is fine because we multiply by m p over 2 times. If I2 takes the same value, wait, how to say this? It's not rigorous yet. Let's make it rigorous. Mm, mm. Oh, I see. So this is actually the worst case scenario. This is the worst case scenario. Suppose there's some indexes appear, let's say 3 times, more than twice, right? Then what you do is you have n choices for this guy, and we have p minus 1 choices for this guy, right? And now you have p minus 2 choices for this guy, okay? You just keep picking it. Let's say it appears 4 times, p minus 3. So the first term becomes n times p minus 1, p minus 2, p minus 3, as opposed to the original n times p minus 1 term. So this is the difference. But now when we move down to the second step, you pick for I2, right? You have n choices, and then you do some pairing, p minus 4 pairing. We do have to do pairing now because in the first one, this value, we exhaust all other positions that has the same value. The thing is that if some random variable appears more than twice, when you look at this number of terms, what it does is replacing a factor of n by some factor of p, which is a lower order term because n is much larger than p. Okay? I will leave it for you to make this rigorous. I don't think, in general, this bound is probably okay. Any question? No, if there's no question, we're gonna end today's lecture a little bit early. So one announcement, next week's class will be moved to the afternoon. Next Tuesday, January 7th. The class will be in the afternoon, 3:30 Beijing time or 4:30 Korean time. Okay. See you next Tuesday.